Alright, let's talk about something really interesting in chemistry, the laws of chemical combination. Basically, when elements react with each other to form compounds, they don't do in a messy, random way. They follow certain fixed rules. Think of these rules like traffic rules for the atoms. No matter where you are in the world, the rules stay the same. There are five major laws. Let's go through them one by one. So, today we are going to start with laws of chemical combination. Laws of chemical combination. How the atoms are going to combine to form compounds using certain set of fixed rules. So, first law, talking about the first law, which is law of conservation of mass. Law of conservation of mass. This is the first law which states that in a chemical reaction, mass is neither created, mass is neither created nor destroyed. Mass is neither created nor destroyed. The total mass of reactants remains equal to total mass of products. Total mass of products. Now, why so? Because atoms cannot be created or destroyed in ordinary chemical reactions, they only rearrange. For example, I'm taking the burning of magnesium in air. Burning of magnesium in air. See, if I'm taking 12 gram magnesium and 8 gram oxygen, 8 gram oxygen, it will give me 20 gram magnesium oxide. 20 gram magnesium oxide. Now see, the total mass of reactants is 12 plus 8, which is equal to 20 gram, and total mass of reactants is already, products is already 20 gram. So the total mass of reactants is equal to total mass of products. Right. Now let us talk about the second law, which is law of constant proportions. Law of constant proportions. This law states that a chemical compound contains the same element in the same proportion by mass, no matter its source or method of preparation. A chemical compound contains a chemical compound contains the same elements, the same elements in the same proportion by mass, in the same proportion by mass, no matter its source or method of preparation, or method of preparation. Now what does it mean? For example, if I take water, H2O, right? So always one part of hydrogen will combine with 8 parts of oxygen by mass, right? Always one part of hydrogen will combine with 8 parts of oxygen by mass. Or if I take any other compound, for example, carbon dioxide, CO2, right? So always the 12 parts of carbon, the 12 parts of carbon, they are gonna combine with 32 parts of oxygen by mass, right? So this shows that compounds have fixed recipes. They are not mixtures, they are pure and definite. They are pure and definite. Now let us move to the third law, which is law of multiple proportions. Law of multiple proportions. Now this law was given by John Dalton in 1803, and it is one of the quintessential laws of chemical combination, which states that when two elements form more than one compound, when two elements form more than one compound, more than one compound, the masses of one element, the masses of one element that combines with a fixed mass of that combines with a fixed mass of the other, a fixed mass of the other are in simple whole number ratio, are in simple whole number ratio. Now let me take some examples. See, if I'm taking two elements, carbon and oxygen. So see, the first compound will be carbon monoxide, in which 12 gram carbon is combining with 16 gram oxygen. Second compound I'm gonna take is carbon dioxide, in which 12 gram carbon is combining with 32 gram oxygen, right? So when two elements form more than one compound, the masses of one element that combines with the masses of the fixed mass of the other are in simple whole number ratio. So if we have a fixed mass of carbon, which is 12 gram over here, the masses of another atoms, which is oxygen, it is gonna give us the ratio of 16 is to 32, which is 1 is to 2. Simple whole numbers. Let me take some more examples. For example, nitrogen and oxygen, right? Nitrogen and oxygen, it forms several oxides like N2O. In N2O, it is 28 gram nitrogen with 16 gram oxygen. Nitric oxide NO, in which 14 gram nitrogen with 16 gram oxygen. Nitrogen dioxide, it is 14 gram nitrogen with 32 gram oxygen. Dinitrogen trioxide, which is N2O3, now it is 28 gram nitrogen and 48 gram oxygen. Dinitrogen pentoxide, which is N2O5, now it is 28 gram nitrogen and 80 gram oxygen. Now if I fix nitrogen at 28 gram, if I fix nitrogen at 28 gram, right? The oxygen masses will be 16, 32, 48, and 80. 16, 32, 48, and 80. Right? So if I take the ratios, so it will be 1 is to 2 is to 3 is to 5, which is what? Simple whole numbers again. They are simple whole numbers. Right. So why this law is important? Because this law provided strong evidence for Dalton's atomic theory, which we'll be covering in the next video, which states that atoms combine in whole numbers and not fractions. That's why we see these neat ratios. Alright, so let us move to the next law, which is law of reciprocal proportions. Law of reciprocal proportions. Now, its statement is sort of bit difficult to understand, but we'll make it do so. This law was given by Richter in 1792. So the statement is if element A combines with element B combines with element B and also with element C and also with element C, then the ratio in which B and C combine, then the ratio in which B and C combine with each other is the same or a simple multiple or a simple multiple of of the ratios in which they combine in which they combine with A in which they combine with A. So if I have to simplify, the statement will be if A forms compound with both B and C separately, if A forms compound with B and C separately, then B and C will also form a compound with each other. B and C will also form a compound with each other in a related predictable ratio. So the compound formed by the B and C will be in a related predictable ratio. For example, I'm taking hydrogen, oxygen, and sulfur. Right? Hydrogen, oxygen, and sulfur. See, we know that hydrogen plus oxygen, they are going to combine to form water, in which we will be taking 2 gram hydrogen plus 16 gram oxygen to form water. So the ratios will be for hydrogen and oxygen, that is 2 is to 16 or 1 is to 8. Right. Similarly, we also know that hydrogen plus sulfur forms hydrogen sulfide. Hydrogen plus sulfur forms hydrogen sulfide, in which 2 gram of hydrogen is required to form hydrogen sulfide with 32 gram sulfur. So the ratios will be again 2 is to 32, that is 1 is to 16. This is by mass ratio. 1 is to 8 and 1 is to 16 ratio is by mass. Right. Now we know that oxygen and sulfur, they also combine with each other to form SO2. Oxygen and sulfur combine with each other to form SO2. Right. So 32 gram oxygen is required. 32 gram oxygen is required with 32 gram sulfur to form SO2. So if I take their ratios, it will be 32 is to 32, that is 1 is to 1. Now see, now you compare the ratios. Oxygen makes 1 is to 8 with hydrogen, right? If this is a scenario, this is our hydrogen, right? It forms compound with oxygen to form H2O in 1 is to 8 ratio. Hydrogen forms compound with sulfur in 1 is to 16 ratio, right? So oxygen has the ratio with hydrogen, that is 8, and sulfur has a ratio with hydrogen, that is 16, right? So their own combination, that is the oxygen and sulfur combination, their ratios will be 8 is to 16, that is 1 is to 2, which is directly related with the ratios with hydrogen. In simple words, if I have to say, if A knows how to bond with B and A knows how to bond with C, then B and C will also bond with each other in a predictable way. Now, why this law is important? Because it strengthened the idea that chemical combination is governed by simple ratios, which only made sense if matter was made up of indivisible particles, that is, atoms. So, this law is one of the quintessential laws for the proving of Dalton's atomic theory. Right. So, let's move to the last law, which is Law of Gaseous Volumes. Law of Gaseous Volumes. This law was given by Gay and Lussac. This law was given by Gay Lussac in 1808, and this is very visual and powerful. So it states when gases combine, they do so in a simple volume ratios, and the volumes of products and the volumes of products if gaseous are also in simple are also in simple ratios in simple ratios, provided all the gases are measured at same temperature and pressure. Provided all gases are measured at the same temperature and pressure. Now remember that this law is about volumes. and not masses. The rest laws which we did earlier, they were mainly focused on the masses, but this law is of volumes. This law is taking the consideration of volumes and not the masses. For example, if we have hydrogen and oxygen, right? So if we have hydrogen plus oxygen, right? So two volumes of hydrogen are required, two volumes of H2 is required to take part with one volume of oxygen to forms two volumes of H2O, right? So its ratio will be 2 is to 1 is to 2. Two volumes of hydrogen taking part with one volume of oxygen to form two volumes of H2O. Definitely this H2O is vapors, gaseous form. So 2 is to 1 is to 2. Or if we want to take some more examples, so we can take hydrogen plus chlorine, in which we know that one volume of hydrogen, one volume of hydrogen is gonna combine with one volume of chlorine to form two volumes of HCl in gaseous form. So the ratio will be again one volume of hydrogen which is combining with one volume of chlorine to form two volumes of HCl gas. Right? So why this law is important? This law clearly showed that gases combine in a fixed whole number ratios. So it gave direct support to the Avogadro's hypothesis, which explained that equal volumes of gases at the same temperature and pressure contain same number of molecules, which is nothing but the mole concept. This is the concept of mole, and this law provided the evidence for the concept of mole given by the Avogadro, that the equal volumes of gases at same temperature and pressure contain equal number of volumes. Right? So to sum up, we have to see that these laws, conservation of mass, constant proportions, multiple proportions, reciprocal proportions, and gaseous volumes, they all tell us one thing, that chemical reactions are not random. Chemical reactions are not random, right? They are governed by simple whole number ratios. So, this neatness is only possible because the atoms exist as tiny indivisible units combining in definite ways. That's why these laws laid the foundation for Dalton's atomic theory and later Avogadro's work. So, if you like this content, please like, comment, and share this video as much as possible. Thank you and happy learning.